Hello everyone, my name is Lakshmi Narayan and I'm from Aero A, roll number 133. Coming to my topic of mechanics of solids, this tech talk is about the design and stress analysis of toroidal field coil of JT60SC or 60SA. This is the rough estimation diagram of next plan of JT60SC, where we have colloidal field coils SC, chirostat, toroidal field coils JT60U, JT60SC. Coming to its introduction, the agreement between the government of Japan and European Atomic Energy Community for the joint implementation of broader approach activities in the field of fusion energy research was signed on 5th February 2007. This so-called broader approach materializes the privileged partnership of Japan and Euratom in the field of fusion energy research. Japan and Euratom will work together on 3 individual projects under this agreement to accelerate the realization of fusion energy as a clean and sustainable energy source for the 21st century. The JT60 tokamak will be upgraded to an advanced superconducting tokamak JT60SA and be operated under the framework of this agreement as satellite facility for ITER. The satellite tokamak program is expected to develop operating scenarios and to address key physics issues for an efficient startup of ITER experimentation and for research towards the fusion demo reactor. After the conceptual design report, it was recognized that the superconducting magnet baseline design presented some cost issues. There were a number of reasons for the cost issues arising with the JTS60SA design. In the TF magnet, they were larger than expected cost of winding, significant increase in amount of superconducting strand to obtain a sufficiently large temperature margin under large nuclear heating. In the PF magnet, they were larger than expected cost of conductor materials and number of coils for unrealistic plasma operation. The cryogenic system had uncertainties in the design, including reasonable sizing of cryoplant distribution and the main equipment. The amount of heat loads, the rebaselining of the machine has been completed to reduce the manufacturing cost. All the scientific missions for the JT60SA project can be achieved with the low cost design machine. Main reductions for the magnet design are toroidal field, number of PF coil and neuron heating. Design of superconducting magnet system for JTS60SA consists of 18 toroidal field coils, a central solenoid, 6 equilibrium field coils as shown in the table 3 and figure 2. The TF coils generate the field to confine charged particles in the plasma. The CS provide the inductive flux to ramp up plasma current and contribute to plasma shaping. The EF plasma current and contribute to plasma shaping. The EF coils provide the position equilibrium of plasma current and the plasma vertical stability. The configuration of JT60SA magnet system is very much similar to the item magnet system because the design basis of these coils have been developed mainly by Europe, Russia, US and Japan during the ITER engineering design activity EDA phase. This is the magnet system of JT60SA where we have the CS, TF coil and EF coil. TF coil. The TF coil case encloses the winding pack and the main structural component of the magnet system. The TF coil inboard legs are wedged all along their side walls in operation, with friction playing an important role in supporting the out-of-plane magnetic forces. In the curved regions above and below the inboard leg, the coils are pre-compressed by toroidal bolts and 2 circular insulated pins. In the outboard region, the out-of-the-plane support is provided by outer intercoil structures, separated with the TF coil cases. The OIS consists of 18 sections that carries a coil and supports it against of the plane loads while allowing limited radial movement due to in-plane expansion of the coil. There is low voltage electric insulation toroidally between TF coils in the inboard leg weighted region and between the OIS connecting elements. Coming to the central solenoid, The CS assembly consists of a vertical stack of four independent winding pack modules, which is support from the bottom of the TF coils through the preload structure. At the top, there is a sliding connection to improve a locating mechanism and support against dynamic horizontal forces. This pre-compression structure provides axial pressure on the stack. It consists of a set of plates located at inner and outer diameters of the coil stack. The number of CS modules is selected to satisfy the plasma shaping requirements and minimize current leads. The modules can be energized independently. The bus bars, joints, and cooling pipes are placed outside the coil. The TF coils support the weight and net vertical component resulting from up-down symmetry of colloidal field configuration. The CS pre-compression structure consists of the lower flange, the upper flange, a set of tie plates, buffer plates, wedge, and connecting bolts. The flange are split into 9 sectors linked by electrical insulated bolted joints to reduce AC loss during the pulsing of the machine. The, the induced voltage across the isolated joints is low. The outside of tie plate region needs to have at least 30% open space in the toroidal direction for the joints current leads the helium pipe arrangement. The preload structure is designed so that it can restrain the maximum vertical separating load of acting on end modules of the stack as well as the maximum inward compression and oil coils push up towards the axis without overall gap giving between the coils or coils. The butt joints are located at the coil outer diameter and are embedded with the winding pack. The individual coil modules are identical but rotated and inverted to form the stack with individual interface plates bonded during tracking. Each winding is formed from 6 octa pancakes and 1 quadra pancake with helium inlets to all joints, helium outlets on the outer surface. In case of GT60SA, it is difficult to use inner bore space for helium readers and insulation brakes. The conductor is cooled from inlet located at outer face via high field region to outlet at outer surface. All cooling pipes are laid to top and bottom of CS assembly to connect headers through electrical insulations. This is the CS assembly where the TF coil attachments, centering structure, winding modules, tie plates, gravity support, and mounting structure connected with TF coils are given and shown below. EF coils are attracted to TF coil cases through flexible plates supporting allowing radial displacements. The EF coil positions and sizes have been optimized for the plasma requirements within the constraints imposed by the axis and ports around the vacuum vessel. Winding packs can use the standard double pancake winding with joints only outside of the winding and helium inlets at the inner crossover. The EF1, EF2, EF6 winding pack shall use a single pancake winding with joints located both inside and outside of the winding because of the conductor length and are beyond manufacturing unit 600 meters. The magnetic field inside the outer surface of the winding becomes similar level. For EF coil, the winding pack consists of a stack of pancakes enclosed on a assembly requirements. Large diameter EF coils shall be manufactured directly on site in Naka because of the difficulties associated to the ground transportation. The top and bottom of EF winding pack is supported between the clamp plates. Two clamp plates shall be tightened by long stud bolts to keep pressure during cool down and magnetic loads. Four corners of the winding pack have the peak stress during pre-compression at room temperature. Clamp plate shaped with cubic function at distance room from the center line of the clamp plate can reduce peak stress in the wild pack. Conductor. All conductor for TF, CS and EF coils are cooled with supercritical helium with a coil inlet temperature of 4.5 Kelvin. All conductors are type of cable in conduct. CIC conductor with circular multi-stage cable, where the measurements of the two conductors given below in the diagram. Feeders. Each coil is electrically connected through in cryostat feeder to current lead located outside the cryostat in the coil boxes. The cooling pipes of the winding and structures are connected to wall boxes. The VBs are installed just outside the cryostat to keep the vertical axis of the maintenance for the port. The cryostat CTBs, VBs and the cryoline are shown in figure 8. For a coil, it consists of feed and return current supplies bus bar. The return and supply helium lines and instrumentation lines. The cryo line is a bundle of cryogenic transfer lines with separated vacuum chamber from the helium refrigerator to the cryostat. A total of 26 current leads using high temperature superconductor prepared by EU Germany are installed in the CTB. The HTS leads are located on the magnetic field 30 MT to optimize amount of HTS materials. The TF coils are connected by 6 coil series with internal SC bus bars, and the other coils are found connected individually. The HTS material is BSCCO 2223 and AGAU stabilizer. This lead consists of HTS section and conventional copper section connected together through an electrical joint. The joint and the copper are cooled by helium gas at 50 K helium. The cold end of the HTS material is cooled by induction to the bus bar at 4.5 Kelvin. This is a conductor assembly facility at NACA site where we have the X-ray welding, compaction, bender and spool. Conclusion: the detailed design of PF coil system was compiled by summer of 2008. This tool for conductors of CS and EF coils are progressed to qualify the trial conductor fabrication. The manufacturing CS and EF coil is started to design the manufacturing tools. The building of EF coil manufacturing is completed. The manufacturing for a trial sample is progressed to verify the detailed components, inlet, joint and termination. And the detailed design of TF coil system was completed by summer of 2009. Fabrication will start in 2010. The assembly of the magnet system, mainly TF coil, will be studied to minimize the assembly period. The detailed design of associated components, the thermal shield, the feeder components and quench detection and control system will be started in next year. Thanking you, and this is the end of my slide.